This is chapter 26, example 2. What we have here, a circuit that drives 4 LEDs with a binary count. The circuit increments every third clock cycle. The circuit also has extra LED output that blinks at a 2/3 duty cycle. Now, this is an interesting problem. I would say there's several ways to do this. It looks like an old problem in that there's a little state machine in there that allows state machines to generate specific duty cycles. That seems like that's something we're going to do in this problem. First thing we want to do is the black box diagram. And so this has a clock input. I don't think it has any other inputs. It has the LEDs on the output. That blinks with the 2/3 duty cycle. So there's 2 LEDs. I think I'm just going to change just the count so it doesn't interfere with the other one. So 4-bit output, a 1-bit output, and a clock on this. First thing we want to do is think about what this circuit has in the interior. It has a counter. So the issue with the counter is the fact that we got to clock it specially. And so let's just drop that counter down. The output of that counter is our final count. What we need to do specially here is increment as this handle this clock, and we'll get to that in a second. And we're going to assume it's up counter. We'll call it counting up all the time. And I think we are done with that. Now, the other part of this problem is it needs a circuit that both handles the LED output. Certainly this counter as is has no way to handle the LED output. So we're going to handle that with state machine. So the state machine is going to look like this. FSM. It's going to be clocked, and the idea here is it's going to have essentially a special clock. We'll call it the slow clock. Okay, and that slow clock is going to be the clock that we clock the counter with. So it's essentially a slow clock because it only increments every third clock cycle. The last issue here is this has an LED output also, so not a big deal. We can handle that pretty easily. Very similar to the previous chapter with essentially the state machine. So what we need here, this needs to be a 2/3 duty cycle. This will start with a state machine that kicks out that duty cycle, and then we'll modify it such that it makes this counter work properly. So not very good state names. So the idea here is it has a 2/3 duty cycle, so we'll call it LED. Now this thing, there's nothing really controlling it, so the transitions are unconditional. So this problem is almost done. We didn't handle this output. Now this output, there's a couple ways to do it. In fact, there's 3 ways to do it. Essentially, I have to, at one point, turn this output on. And it doesn't really matter which state I turn it on, but it's going to be turned on in one of the states, and it's going to be turned off in the other 2 states. So this is slow clock and slow clock. And I think we'll leave it on. We'll leave it on in that state because I ran out of room. And it's off in these 2 states. So only one of these states, this slow clock asserts. When it asserts, it provides a rising edge for this slow clock here, which increments this count. So this circuit is officially done. We'll check it over. Notice I didn't connect the control signals or the status signals. This is logically connected to there. I logically connect them with names only. Each one of these states accounts for both of the outputs. It works very well as a Moore machine. I guess you could do it as a Mealy machine, but it would make no sense. This is the way that makes the most sense. Once again, the LED is on in 2 of these states and off in 2 of those states, which gives me the 2/3 duty cycle of LED. One of these states generates a clock cycle, a signal that's used as a clock cycle for the counter. That's going to be my count that only increments every 3 clock cycles. So it's every 3 of these input clock cycles. And at this point, we will say this has a state machine in it, so it's circuit controlled, and it has this input here, which is a control input for a counter. We can argue that it's also internal control. Call it done.